Alrighty, guys. So now that we know a little bit about acids and bases and kind of like the reactions that they tend to do, we are going to start looking at what we do with acids and bases. And one of the things that we do is this thing called a titration. Now, titration is basically what we do to figure something out, like how concentrated this unknown acid or base is. Like if somebody comes in with a big, I don't know, jug of water and they're like, oh, we found this in this giant weird tanker, we need to know how acidic or basic it is. We need to know what the concentration of this acid or base is. Well, first thing we do is take some litmus paper, bloop, and we find out if it's going to be, acid or base, because we know bases turn blue, and we know that baboons have red, acids turn litmus paper red. So, we'll know if our unknown solution is an acid or a base. So let's pretend that we have an unknown solution of an acid. Right? So it turned litmus paper red. So what we're going to do is we go in the lab and we prepare very, very carefully, very precisely, a concentration of a base. So we know that we have this base, we know its concentration very precisely, and what we do is we go ahead and perform a neutralization reaction. And the thing is that with acids and bases, it's one hydrogen for one hydroxide. So if we know how much base we used to neutralize it, like if we know how many moles of hydroxide we had to add to neutralize it, we'll know exactly how many moles of hydrogen are in our unknown solution. Pretty easy to figure out the concentration after that. Let's just dig right into it, guys, and we'll get some titration knowledge going. So, first thing we need is the definition of a titration. And like I said, it's basically a method for calculating the unknown concentration of an acid or base by neutralizing it, right? So this is like an acid-base neutralization reaction with a solution of known concentration. It's like a neutralization reaction. We've done this like ad nauseum. Everybody seems to be spot on with this. So here's how it works: a volume of an acid or base, right, is added to a known volume of, but we're not sure what the concentration is. Whoops. So what we do is we take a volume of a known concentration, okay? So here, this means that we know the molarity and we know the volume. You got it? And we add that to a known volume, but we don't know the concentration. So that's going to give, so here we have volume, but the molarity, we're not sure. And that's basically how titrations work, right? So we have the concentration and volume of one that we know for sure, and we have a volume that we know, because, we can measure it out. We just measure out a small sample, but we don't know how concentrated it is. You dig? And the reaction is really, really simple. It is one hydrogen reacts with one hydroxide and makes one water. So it's a 1-to-1-to-1-to-1 ratio. It's lovely. And so, well, what this is like the number of moles of hydrogen, and this is the number of moles of hydroxide. And to figure this out, right, and if you notice, 1 is 1, these are equal, right? So this idea right here, that the reaction is a 1-to-1 ratio, gives us this thing, and this is the titration equation. And this is found on the back of your reference table, and it works like this. The molarity of the hydrogen ion multiplied by the volume of that acid is equal to the molarity of the base multiplied by the volume of the base, of the hydroxide. And I kind of want to make that really clear, that these molarities here, these are not the molarity of your acid or your base. It is the molarity of the hydrogen ions, and it's the molarity of the hydroxide ions. Because if you take a gander up here at this and this right here and here, if you'll notice, it's the hydrogen and the hydroxide ions that are doing the reacting. So those are the things that we want to watch out for. That's the concentration that we need to know. And I want you to lock that in, because it'll be pretty easy at first, but then it'll get more complicated. It always gets more complicated. You get it? So this is the MAVAB-MUVVUB equation. MAVAB-MUVVUB. MAVA equals MBVB. And it's super simple. There's going to be one unknown, and typically it's going to be the molarity that is unknown. If this was like a real titration, it's the molarity that we're actually searching for. you know? So we'll have three. We'll have three variables. You have to solve for the one. But the real trick here is to remember that this is the molarity of the hydrogen ion, and this is the molarity of the hydroxide ion, because some acids produce 2 hydrogens, some bases produce 2 hydroxides or more. It gets all complicated. So here's how this works. You don't need to memorize this, but I just want you to see it so you can kind of have an understanding of why and how this equation works, right? Keeping in mind, and you have to keep in mind this thing. Maybe I'll clean it up so you can actually see it. That it is a 1-to-1 ratio of hydrogen to hydroxide, okay? So the way this works is here is the concentration of your hydrogen ions, and there is the volume of your hydrogen ions. And here, like I said, this is the concentration of hydroxide ions, and here is the volume of your base. Now, how do we measure concentration? Well, if you remember way back in the last chapter about solutions, we learned how to calculate molarity, right? Right, molarity, or like capital M. It is calculated as moles per liter. That's the definition of molarity, right? So the same thing over here. The concentration of the hydroxide in molarity is moles per liter. That's really cut and dry and simple. And volume is liters. Like liters is liters, right? So what we end up with here is on the left, it is moles of hydrogen ions divided by liters times liters. And on the right-hand side, we have moles of hydroxide ions per liter times liters. So you see all the liters cancel out, and what we're left with, is moles of hydronium. Moles of hydronium equal moles of hydroxide. Right? And they have to be equal. They have to be perfectly equal because it is a 1-to-1 ratio of hydrogen to hydroxide ions that make a neutralization reaction happen. So let's just dig into some problems, man, because the idea of this being like a 1-to-1 reaction is pretty simple. But what's not really super straightforward is exactly how to go about doing these. And what I recommend we do is we read the problems, and then out on the side, like somewhere over there, I want you to write out the variables that are given to you in the word problem, including the one that you need to know with a little question mark. And then we'll see if we can just figure it out on our own. And then if not, I guarantee there's some kind of equation in the back of our reference table to help us. So let's just do it. Let's do it with this color blue. Okay, so how many moles of hydrogen ion? That's my question mark. I know that because they're asking how many are needed to neutralize 2 moles of OH. Okay. All right. Well, this one, there shouldn't be any math in this one because we know that it is 1 hydrogen to 1 hydroxide. The answer is 2.0. It has to be that because hydrogen and hydroxide react in a 1-to-1 ratio. Delightful. Next one. Let's see. How many moles? Oh, right there. How many moles of OH? So I'm going to come over here. There you go. Moles of hydroxide. That's my question mark because that's what they're asking. So how many moles hydrogen peroxide are needed to neutralize 200 milliliters of 8 mole HCl? Okay, so I've got 200 milliliters and 0.8 molarity, and this is HCl. All right, well that's weird because I'm given all I have here, like what I've got is a bunch of information, but it's only about the acid, right? But they're asking how many hydroxides. Well, this problem is almost exactly like the one right up above. Let's go back up to this other one. This other one here is asking how many hydrogens per hydroxide. Well, if you remember, it's a 1-to-1 ratio. But for this one, they just flat out said, hey man, 2 moles of hydroxide. They just gave it to you, right? Now this one, they're turning it up a notch. Instead of just giving you how many hydrogen ions are here, we're going to have to figure it out somehow, right? We're going to need to figure out, well, how many moles of hydrogen ions are here, because that will tell us exactly how many moles of hydroxide we need. Okay, so that gives us this little side quest here. So we got to find out how many hydrogens. Well, if I've got volume and I've got molarity, if you remember this equation, molarity is moles per liter. So I can figure out how many moles of hydrogen we have, right? Because if my molarity is 8 and my volume is 200 mils, it's going to go like this. 0.8 equals moles per You didn't use 200, did you? You knew I wasn't going to do that, right? So the moles of OH is going to be 0.16. Got it. That equals moles of hydroxide. You guys follow how that works? It's just like if I have 10 moles of hydrogen, how many moles of hydroxide do I need? 10. Easy. This next step, okay, well, instead of just flat out telling you how many moles there are, we're going to make you figure it out by giving you a volume and a molarity. And it's pretty easy to figure out the moles, right? This thing, like, we have done this a lot of times. So it's just you just got to figure out how many moles first, and then it's a 1-to-1 ratio. All right, let's see how they try to make this next one more difficult, because you know that they're going to try to make stuff more difficult, of course. All right, here we go. Ooh, my face is in the way here. There you go. Okay, if we needed to neutralize 150 milliliters, let me write this down right here. 150 milliliters of 3.0 molarity. Okay, this is an NaOH. And here's another little trick that I do, because you know, reading in my eyes, we don't get along very well. So what I also tend to do is I will underline important words. Okay, neutralize. That just means that we're canceling out, right? So however many hydrogens I have, that's how many hydroxides I'm going to need. All right, so let me get back here. Okay, if we needed to neutralize, important word, 150 mils of 3 molar NaOH, how many moles of hydrogen would we need? Well, this one is exactly like the previous question, only a little bit different, right? If we're asking how many moles of hydrogen ions we need, right? First thing we got to figure out is how many moles of hydroxide we got, right? Because it's a 1-to-1. But again, we're not directly given the number of moles. We are going to have to use this wonderful equation and plug and chug. 3.0 for my molarity. And remember, the milliliters, they're lovely, but we can't use that in this equation because, as you can see right here, it says very clearly, it says liters, not milliliters. So I'll switch that right quick. So I have 0.45 moles of OH. So that's how many hydrogens I'm going to need. Easy peasy lemon squeezy. All right, I'm waiting for something to get difficult here. All right, so maybe this is a little more difficult. But I have a feeling that there's going to be a way to figure this out. Because the first thing I'm going to do whenever I have this, like something like this, I'm going to start underlining. I'm going to start writing out the variables. We're going to figure it out. All right, so how many milliliters? So how many milliliters of a 1 molar HCl? So I've got 1.0 molar, and this is HCl. Are needed to neutralize. Okay, 200 mils of 2 molar NaOH. All right. So for this one, once again, we got to figure out, like, we got to make the hydrogens and hydroxides equal. But now I've got something, there's a lot of variables here, right? I've got concentration, I've got volume, I've got concentration, I've got volume. Is there an equation that we learned about that might be able to help us out with this? Oh, yeah, right. Do you remember the titration equation? Yeah, this is the kind of thing where the titration equation is going to be super duper helpful, where, you know, we've got a volume and a concentration of one, and we've got like concentration but no volume of the other. Here's how this is going to work. We're going to first write MAVA equals MUBVUB, and we're going to check this out. Okay, so the molarity of my acid, here, that's this, is going to be 1, is 1.0, and the volume of my acid is something I don't know yet. So we're going to figure that out. But my base, I have everything I need to know about my base, right? The molarity is 2.0. And the volume, I'm just going to switch it to liters just to be on the safe side. You don't have to, but you should. Just to be safe. And now, again, what this is saying on this left-hand side, molarity times volume, that gives us moles of hydrogen. And on the right-hand side, molarity times volume, that gives us moles of hydroxide. So again, they should be equal 1 to 1. We're just using that trick to figure some stuff out. So let's figure this all out. We've got, okay, so that means the volume of the acid is going to have to be 0.400 liters. Just like that. And that's your titration equation there, right? So again, this one is like the first three were, hey, if I have this many hydrogens, how many hydroxides? It's easy. It's a 1 to 1. Here, the last two, they kind of mixed it up a little bit, tried to make it a little bit more difficult. By instead of just like directly giving you the number of moles, they gave you like volume and molarity, but that's easy to figure out moles from there. Now this one, they didn't give you any clue. They're just like how much, they gave you the volume and the molarity for your base, and but now to complicate it, we now have a 1 molar solution, right? So the question is what volume do we need to make sure that we have that 1 to 1 ratio? And to do that, the titration equation, and that's it. All right, let's see this again. All right, how much is volume? So the volume is going to be a question mark of 0.1 molar. So that's my acid. Is needed to neutralize 2.0. Ooh, I said that wrong. I said just 0.2 liters of 0.3. All right. Same exact thing here, guys. Same exact thing. Okay. We're not sure. Again, we want it to be a 1 to 1 ratio. We're not sure the volume, but we do have a concentration here for the acid. We have both a volume and a concentration for our base. So we just want to know what volume of acid we need to have so that we have an equal number of hydrogens and hydroxides so that they are both neutralized. Right? The equation, super easy. Mavab mubvub. Mavab. Mubvub. Now let's do a little bit of substitution here. So the acid is going to be 0.1 for my concentration, and we're just going to leave it like that because that's like we'll figure it out later. The molarity is going to be 0.30 for my base, and the volume is 0.2 liters. How nice of them to leave it as liters. Okay, a little bit of stuff here. Was that 0.6 times 0.1? Let me go double check my work. Ooh, I think I did that wrong. I was wrong. I was totally wrong. There you go. 0.6 liters. Got it. We good? Sweet. I mean, that's it. Like, that's it. That's all there is for the titration. Oh. Okay, maybe there's more. There's always more. Nature. Okay, so look. Polyprotic acids and polyhydroxy bases. So if you look at these acids and bases that we had up here, these ones are all like super easy. Look, 1 hydrogen, 1 hydroxide. Ooh, hold on. 1 hydrogen, 1 hydroxide. Man, you know it's not going to be that easy. Nature is not just all simple, easy, cut and dry, black and white. Never. So there's a little trick we have to do here when we're doing titrations with when there's more than 1 hydrogen or more than 1 hydroxide, which is what polyprotic and polyhydroxy means. Okay, so let's just, instead of explaining how, let's just dig into it. Okay, so what is the concentration? So this is going to be our question right here of an HCl solution of 30.0 milliliters. This acid is neutralized with 50 mils of 3 molar calcium hydroxide. Now look at this. Do you guys see this too? You guys see that? Here, I'm going to like really make sure that everybody sees it. And then you have to look at that. and then look at it. I want you to look right at it. Would you look at that? I want you to look right at it. That is a problem, because if we have a 3 molar concentration of calcium hydroxide, that is not the concentration of the hydroxide ions. That is not the concentration of the hydroxide ions. And here is how that works. If you have 1 calcium hydroxide, that is, right, how many hydroxide ions do you have? You have 2 OHs in there. Do you dig what I'm saying? Because when that starts reacting, there are 2 hydroxides that will react. So for every 1 calcium hydroxide, there are 2 hydroxide ions, right? So if you have 2 calcium hydroxides, it will create, or it will make, 4 hydroxide ions. Do you dig what I'm saying? So if your concentration is 3, you have to multiply it by that little subscript. You got it? So this equation is going to be modified like that. We're going to take that subscript and we're going to multiply the concentration by that subscript, because for every, in this case, for every 1 calcium hydroxide, you get 2 hydroxide ions. So it doubles the concentration of the hydroxide ions in solution. You guys dig what I'm saying? So it's an easy fix, man. So like you just take a 2 and you just pop it right in there. So instead of 3, right, you will end up with 6, because that's the actual concentration of your hydroxide ions. Then everything else like works out just swimmingly. You guys got it? Let's try one here. How many milliliters? So that's going to be a question for volume. So volume equals question mark. And molarity is 0.50. And this will be for H2SO4. Is needed to neutralize. Okay, I've got 100 mils of a 2.5 molar solution of KOH. You guys see it? You guys see that? Right? Gotta keep, that's, you if you don't catch that, man, your life is going to be more difficult than it needs to be. But everything else works the same, right? So this is just like the other titration. So I'm going to write out my mab, but I'm gonna edit this right quick before I go anywhere. Because I have this 2, I'm gonna pop that right in front of the concentration for the acid. And everything will work out lovely. Right? Because H2SO4, the sulfuric acid, you put 1 sulfuric acid in there into the water and 2 hydrogens pop out. Right? So it's like the hydrogen ion concentration is actually double the concentration of the entire acid itself. Works out like this. Where's my math? Okay, so it'll be 2 times 0.5. So it's 2 times 0.5 times the volume of my acid. And now the magic of math. 0.25 liters. I hope I did that right. My calculator says that right, so it must be right. You got it? You guys see how that works? Again, the only thing you really got to watch out for is this. You got to watch out for those subscripts, because those subscripts mean that like you've got more, it's more than a 1-to-1 ratio for like the concentration of the acid versus the concentration of the hydrogen and hydronium ions. Oh, whew, nice. All right, so we have, man, well, we're going to start with 2, but there may be more. We've got titration word problems, and we've got titration multiple choices. Man, we are going to learn about titrations, folks, and I hope that I hope the rest of your day is just peachy keen, because mine's looking like it's going to be just like that. So I will see you guys very soon, later.